Good morning, everyone. I would like first thanks to organizer for giving me this opportunity to be here in this nice conference and a great gathering. So, I am Shivangi Sri from IIT Patna. I will be presenting some of the work that I did during my PhD as well as in postdoc. I recently, now about 2 years, moved to IIT Patna, and currently I am setting up the lab. So, I will show some results from my past works. So, as you know, I will briefly introduce, sorry that you have already know all these, but to complete the topic, I would like to introduce again. So, this field started from the isolation of graphene from graphite, and which led to have Nobel Prize in 2010, and after this field just blew up. So, why it is so? Because the properties that you find in bulk of these crystals is very different as you thin down to a single atom thick layer. So, and it is really a very simple manner we can thin down and get a isolated layer which are atomically thin because of this weak van der Waals interaction that takes place in these layer materials. And because of this interesting property, you can also not only get the homo layer stacking, but also can get hetero layer stacking, which means that you can combine different layers on top of each other and get the hybrid properties which you do not find in the parent crystals. Okay. So, in the bulk form, these has indirect band gap. You do not see much of luminescence coming off from the bulk. Even in bilayers also, this does not emit much. But as soon as we go to a monolayer limit, the band gap becomes direct, and that is why you see a huge luminescence coming out from a single layer here. And all these transition metal diachalcogenides, which are semiconductor, most commonly are molybdenum sulfide, tungsten sulfide, and selenides. These emits in visible range, so that is why it is also very much interesting for optoelectronic devices. So, most of the fundamental properties of exciton in these materials are basically these are Coulomb bound electron and hole pairs, and these are very strong compared to conventional like excitons which you found in 3-5 semiconductors, because they have very large binding energy, 2 orders of magnitude larger than the 3-5 semiconductors exciton. So, this is why, because we have a 2D confinement, also the large effective carrier mass and reduced is dielectric screening. And similar like in hydrogen atom, in these material we see exciton which has, let us say, a ground state and then a higher energy exciton states that we can probe optically. So, what we do? We take a bulk crystal, very high quality bulk crystal, then do exfoliation using dye transfer method, and then do optical spectroscopy very detailed to characterize these excitonic properties and try to engineer further how for different applications. So, this is what we do. So, there are many interesting studies already have been done using the van der Waals heterostructures. For example, you can combine this semiconducting material with magnetic material and then look at the interesting properties. One can make LEDs out of the monolayer WS2s on here, and then one can also couple very easily integrate on silicon photonics, or here in this case silicon nano resonator. You just stack them on top of each other to enhance further the luminescence. And then the theme of this session about the Moire superlattices, one can also try to study the correlated states or also looking for single photon emitter, for example. So, this is the part where we do exfoliation, then just transfer this on. This is a home built setup that I used, and in the optical microscope you can identify the layer thickness. Of course, AFM or PL will be useful, to further confirm the layer thickness. But just by contrast, because these has very high absorption, so just by looking at the contrast, you can in the first glance you can see whether you have monolayer or not. So this is the optical setup where we can do all the like polarization dependence, PL, reflection, temperature and all these kind of. So this is my goal right now, to build this kind of setup so we can start doing some cool physics. So in monolayer, as I mentioned, that this exciton has very large binding energy. So this is MOS, different TMDCs, WS2, MOS2 and selenide sulfide, and this you can see up to room temperature A and B exciton. But in monolayer, you see that there are two excitons, two types of exciton which forms. One is intralayer exciton that yesterday Achay has very nicely demonstrated. So here in monolayer you have intralayer exciton where electron and a hole sits within a layer. So you get around negligible out of plane electric dipole moment. That means when you apply electric field, you are going to see a negligible shift. Okay, but still you have high absorption here in the for the exciton. But when you switch to, let's say, homo bilayer, now you see other than intralayer exciton, so that also forms within each layers, but you have electron sitting in one layer and hole into another layer, and that forms another Coulomb bound pair which is intralayer exciton. So in this one you have out of plane electric dipole that you can see easily in the schematic, and then when you apply electric field you can tune this feature very broadly. So this is the work that we started looking at homo bilayer of MOS2. So in this sample we have partially monolayer, and then here you have bilayer. So here the lower spectrum is for monolayer where we see A exciton and B exciton, and then this is the reflection measurement. We have here in the red curve we see a very strong feature which I have labeled as interlayer exciton. We were very surprised because we did not have idea that time that what is this strong feature in absorption, because absorption is the measurement where you have very less likely to form another kind of particle. So these are pure like excitons. So this was very strange, and interestingly we see this even up to room temperature. So this was very strong absorption. So then we asked this question, where is this exciton is coming from and what is the like properties of this exciton. Then we contacted our collaborator. He performed some calculation, and then we understood from his calculation that in 2H stacked homo bilayer, we have this kind of scenario. Electron sits in the conduction band and hole hybridized in the valence band. So the exciton that we see in this reflection, so this is just Kramer-Kronig relation that just tuned taken from reflectivity measurement. So I have plotted here. So this is again A and B and this exciton. So this is not a pure exciton like we see usually in heterobilayers. Instead it has some hybridization from the B exciton. So this is kind of mixed state, and this is why we see very strong absorption for this exciton, because some absorption is coming from the B. Then this was done on like a commercial sample, like exfoliated and then taken. Then I also wanted to do because you know that we always focused on wafer scale production. So I tried to do and then on CVD grown sample the same thing. So here we have two different stacking, as you can see 2H and 3R. 2H is when the angle is 180 degree between the two layer, and when it is 0 degree it is 3R stacking. So we expect to see in 2H only this interlayer exciton, because hole hopping is allowed only for 2H, not for 3R. So this is why it is absent here in 3R case. And why I did this, because I wanted to do this manually and see whether how much this CVD flakes are how clean are they. So this was as grown shown in the left, and then I manually transferred as grown monolayer and made 2H and 3R stacking. So, 0 degree and 180 degree aligned bilayers. So, all these 3 are stacked, manually stacked sample does not show any interlayer exciton, and all 3 samples which are manually stacked in 3H form, they show this interlayer exciton, and this experiment shows that the interface is really clean even though we use the as grown sample and then piled up together manually. So, from here we calculated now the interlayer interaction between the two in 2H stacking. So, when this interlayer exciton forms in 2H stacking, this is because of the valence band interaction, this has larger energy compared to 3R. So, from there we calculated this interaction energy, which is about 50 MeV. And the interlayer exciton that we see in 2H homo bilayer, then I made another sample with the gated device to see really the characteristic feature, that the stark shift, and here we have at 0 field. So, this is reflectivity measurement as plotted as a function of field. So, here we have A exciton, B exciton intralayer, then we have interlayer exciton which is degenerate at 0 electric field. So, both are like electron sitting in the top layer and then hole is in the bottom layer, which are hybridized, and then you have electron sitting in the bottom layer and hole is hybridized in the again 2 layers. So, that these are 2 degenerate states at 0 electric field, but when you apply some electric field you will see the splitting. Okay. So, this is what we see here, and as this interlayer exciton has some mixing with the B state, we also see some anti-crossing and very strong coupling between the 2 states here at higher fields. And this type of physics other than the homo bilayer system, then later on also shown in other heterobilayer system, where you choose the 2 layers in such a way that either conduction band or valence band are hybridized. So, you can form a hybridized interlayer exciton, and one can say get the high absorption energy shift for interlayer exciton. And these are interesting for, let us say, Pleuritron interaction, where you need high absorption and a strong shift in energy. These were work with linear optics. Some work also was done on nonlinear optics. So, this is now coming to second harmonic generation. So, in this measurement what we do is you shine the sample with let us say frequency omega, and you collect the twice of the frequency, which is second harmonic generation. So, usually in these kind of 2H stacking, the symmetry is restored. It is not broken in homo bilayers. In monolayer it is broken, and odd numbers of layer it is broken. So, you see strong second harmonic signals for odd numbers of layer, but naturally for even numbers of layer you do not see. So, in this experiment what we did is, this is the again usual reflection measurement on homo bilayer MOS2 directly grown on silicon oxide. So, we have A exciton, B exciton, interlayer exciton. Now, to collect this second harmonic signal, what we did is we tuned the laser energy to across these exciton resonances. So, each spectrum here are taken at different laser excitation energy. So, here what we see is the enhancement of second harmonic when we hit with the resonance, exciton resonance. Now, this got a question, we got this question now, that where this second harmonic signal is coming from, because it is naturally 2H stacking. So, we do not expect any second harmonic. So, then I try to make this structure symmetric, maybe asymmetry is coming from the structure itself. So, again I put HBN encapsulation on top and bottom. So, this expectation was true. Actually, we see some decrease in the intensity, but still there are measurable intensity, signal for SHG, and from here you can see different excitonic resonances which are taken in SHG. And so one tuning parameter is from the previous slide. You see that when you tune the laser energy and get the across the resonance, one can tune the second harmonic response. In further in this device, because we have also control over gates. So when you apply electric field, for this is the blue ones are taken for different laser energy second harmonic. So there are slight enhancement over the resonance, but as soon as we apply the electric field very little, we see a huge jump in the second harmonic signal. So this is because the two degenerate interlayer excitons which are at 0 electric field, now you apply some finite electric field, they are going to move in opposite direction that we have seen in the absorption plot with electric field. So that gives you the enhancement in the second harmonic signal because they are moving in different direction. So overall signal you are adding up each times. So here is the SHG signal plotted as a function of electric field. The black triangle are representing the intralayer exciton, and then we have quadratic dependence for interlayer exciton. So this increases very significantly compared to intralayer exciton, because intralayer exciton does not have this kind of degeneracy, lift in degeneracy. So this was on homobilayer. Now coming back to heterobilayer. So in this heterobilayers, the interlayer exciton that we see is purely interlayer exciton, which means electron sits in one layer and hole resides in the other layer, and it forms this Coulomb bound electron and hole pair. And you know that you can get with the twist angle and lattice mismatch, you can play with the Moire superlattice. And this gives a very interesting physics furthermore, like you can have correlated electronic states, you can have single photon emitters localized on these superlattice sites, and there are many degrees of freedom such as like twist angle, you can play with duping, we can play with the let us say different material combination and like lattice constant. So there are lot you can do with these kind of heterostructures. So people has already studied like shown in a localized emitter, this is theoretically shown, and there are like electron and hole generated Wigner crystals, Mott insulator and exciton crystal. So our aim here is to show exciton crystals, okay, so correlated state of excitons. So one of the theory prediction is that potential energy is proportional to 1 over r cube, whereas kinetic energy depends on over r square. So for enough large density of exciton and lower value of r is basically this spacing between the two sides here. So for lower value of this r, we expect to crystallize this interlayer exciton. Okay. So similar like for holes here shown in around 2023, there are like Mott insulator, and this work was done also for interlayer exciton insulator. But in this work, what they did is they dupe individual layers. It is not like optically they form interlayer exciton, what we usually do, but these are instead individually each layer are duped to form interlayer exciton, and then at different filling of this they see this interlayer exciton insulator. So the goal here was to optically probe this and get the interlayer exciton crystal. For this we made this tri-layer device here, WS2 MOSE2, in between WSE2 MOSE2 we put HBN monolayer just to kill the monolayer in between this layer, and we want to use the Moire from this layer WS2 WSE2. So the idea here, the interlayer exciton which forms between these two layers, we will see the half of the Moire of this, and then we will try to see the exciton crystal. So at 0 electric field, the lowest interlayer exciton is from WS2 WSE2, but as soon as we provide some field, this will be lower down, and then the lower state of interlayer exciton will be from WSE2 MOSE2. So this is the complete device. We use a pickup method to fabricate this. and this is with monolayer BN here, and then this is the top structure, this is the bottom BN with some electrodes, and this is with this is the complete top structure, and then we put together on the bottom structure to get this complete stacking. And here just with top gate, and this is without any gates. So this part is the tri-layer part, the cyan color one, and this triangle here is the one bilayer MOSE2 WSE2, and this triangle here, small triangle, is WS2 WSE2. So this is the color map, like PL image of the heterostructure. So this is the tri-layer part, and this is the WSE2 MOSE2 interlayer exciton. So on the bilayer of WSE2 MOSE2, we try to see the interlayer spacing, which is about 0.5, and then on bilayer of WS2 WSE2, this is also around 0.6. And this is the interesting part where we were interested in tri-layer of whole combination here with BN monolayer. So it is really difficult to see actually this feature here, because now we to confirm that with it is really coming from this combination of interlayer exciton, not this one. On tri-layer part you have different dipoles. So again you will get different shift when you apply electric field. So I have saturated this one to see clearly the other interlayer exciton. And then to show the sample quality, we also see somewhat insulating state for on this bilayer part of WS2 WSE2, and also on tri-layer part also we see. So this shows that after putting this kind of further stacking, we didn't kill the moire of WS2 WSE2. And this is from in the reflection measurement, we also see this kind of Mott insulating states. Now very quickly I will show the exciton evidence of exciton insulator. So in this measurement what we did, we strongly signed the continuous wave light on the sample, and then we sign weak light on the sample. So with pump the stronger light, we collect 1 PL, and then we sign the probe light as well with a very small power to just increase further the small carrier density, and then we just taken the contrast of those PL and then plotted here as a function of power. And when we, for a very small power, when we increase the carrier density, we see that at this power it just blue shifted. So that indicates that we have the feeling of, and when we calculated the exciton density here, it matches very well that the feeling we have is 1. So that indicates that we have a exciton Mott insulator in this sample. So to just summarize this talk, we saw that interlayer exciton has very strong absorption, and one can tune by electric field in homobilayer 2H, and then we can also tune the second harmonic generation for those interlayer excitons. And then we have some evidence of bosonic crystal in WS2 MOSE2. Currently I am starting working on this 2 projects. One is engineering quantum confinement in 2D materials, another one is on many body interaction in ultra thin 2D magnet and semiconductors. If anyone interested to join these 2 projects, feel free to write me. And at the end, I would like to acknowledge my supervisors, Insa Toulouse, Bernardo Bazek, Hong Kong Park in Harvard, and then Andrea Tatsuni for providing the CVD grown samples, and then high quality HBN was taken from NIMS. Thank you.
Okay, thank you for the wonderful talk. Session is open for questions.
So I have a question about like so many stacking, like 6 to 7. So when we what we feel also, like when we have lots of stacking, lots of bubbles come, right? And bubbles also create some kind of strain. So sometimes we saw like maybe it's coming from the strain, the internal exciton, yeah, to the material. So can you comment on this or like how you
Yes,
sure this is going?
definitely. So if you look at, for example, this PL map here, you can see that it is not completely homogeneous. This is the tri-layer. So some part these are bubbles where some layers are not coupled, right? So we try to take the measurements where we see the nice, image of the sample. Yeah.
Yeah, Shivangi, very nice talk. So, two questions. One is, why are you getting SSG for the bilayer at the exciton resonance?
Yeah, very good question. So in these bilayers, even in monolayer, we have studied that when you go across the exciton resonance, you see enhancement in second harmonic signal. So that is in this case where we hit the exciton resonances, that is because of the exciton mediated second harmonic. So there is some phase mismatch happens in the structure when there is like a exciton there, and that second harmonic that we see is really like very small, but is there when we try to make the structure symmetric. So this second harmonic that we see here in 2H stacking is it's basically from the asymmetry in the sample. But for example, if you look still like, if I can go back. Yeah. So in this one, you see this structure. This is quite prominent here. You see more second harmonic when you hit the resonance, but here the signal strongly decreased by one factor, or order rather. So here we try to make the structure symmetric. So the light going inside and coming outside should not have any phase difference. Okay, should be like completely killed out. So in order to get 0 SSG. But here still we have asymmetric from the silicon and silicon oxide.
I mean, it might be interesting to think more about this because even your 2S exciton is showing up. Actually, it's even better.
Yeah, because yeah,
I guess now your H wing encapsulation makes sense.
yeah, it is more like sharp.
Fine, fine. I didn't totally understand the second part, which was this exciton diffuse.
Exciton mediated
Exciton diffuse. What are you trying to say there?
So there is some contribution from exciton. I can show you some theory calculation we have. So there we can look at. So there is some phase relation which comes due to exciton when you are across the resonance, and that is why it is called exciton mediated second harmonic. Any other question?
One last question. If not, let's thank the speaker again.
Thank you.